Imagine driving beneath the ocean floor. Millions of tons of seawater press down above you, while beneath your vehicle lies a seamless fusion of concrete and steel, assembled with near microscopic precision. It sounds like a scene from a science fiction movie, but in fact, it's a real marvel of modern engineering, the undersea tunnel. But how did humans manage to build such colossal structures in such a challenging environment, one characterized by crushing water pressure, unstable sediments, and total isolation from the surface? In this video, Massive Minds will take you deep into the structure, process, and strategy behind building undersea tunnels, one of the most complex technologies on the planet. In the 21st century, transportation is no longer limited to dry land. With over 14,000 kilometers of coastline and hundreds of port cities, China is an economic power built on logistics, home to the largest maritime infrastructure system in the world. Every passing minute, thousands of containers leave their ports. 60% of the global economy depends on the flow of trade through logistics. Yet this raises a fundamental question: how can we maintain uninterrupted connections between the mainland and distant islands without relying on weather, ferries, or sea bridges? The problem may seem simple, but it's the lifeline of an entire economy. When a transport route is disrupted by a storm, fog, or typhoon, it's not just cargo that's delayed. The entire global supply chain suffers. This is especially true at critical ports like Zhuhai, Shenzhen, and Hong Kong, where even a minute's delay can cost millions of dollars. So, what's the solution? Not airships, not traditional sea bridges either. The answer is to build underwater tunnels cutting through the seabed, which is the bottom of the ocean, connecting land and islands to create underground arteries where traffic never stops. But here lies the paradox. Humans want to build tunnels beneath the sea, but the seabed is a place that does not allow for mistakes. Enormous water pressure, unstable geology, strong currents, and complete darkness mean there's no room for trial and error. A single crack could trigger an unimaginable disaster. So why did China still dare to take on this challenge? Because they understood. Mastering the technology of undersea tunneling means mastering not only economic connections, but also gaining strategic advantage across the entire region. Want to build a tunnel beneath the sea? You don't start with concrete or excavators. Beneath those calm waters lie thousands of years of geological movement, layers of limestone, marine mud, and shifting sediment that move millimeter by millimeter each year. One wrong step in surveying, and the entire project could collapse. That's why the pre-construction phase is often compared to a full-body diagnostic surgery. No drill touches the ground until engineers know exactly what they're facing. It all begins with a detailed survey of the seabed. Specialized ships scan the entire area using sonar reflection to create a 3D model capturing every ripple and trench in detail. Then, small drilling probes are deployed to collect soil samples to check for stability, load-bearing capacity, and corrosion risks. Most importantly, they must hunt for hidden dangers, such as geological faults or methane gas pockets buried deep beneath sediment, which could cause explosions if struck by drills. At the same time, another critical question must be addressed. How can we build without killing the marine ecosystem? The sea is not a space. It's home to thousands of species. Piling, blasting, or dredging the seabed can create industrial noise that destroys the hearing of whales, bleaches coral reefs, and throws the entire ecosystem into imbalance. That's why environmental specialists must design compensatory solutions, building artificial coral reefs, installing noise reduction nets, and conducting real-time biological monitoring to temporarily pause construction when large schools of fish pass by. This is no longer just construction. This is a negotiation with nature, where technology and ecology must learn to speak the same language. A millimeter off in surveying, or a decibel over the sound limit, and $1 billion project could become an ecological disaster. After fully understanding the seabed, China moved into the most challenging phase, building a solid tunnel not on land but directly beneath the ocean floor. The first method chosen was the immersed tube method. Each tunnel section stretches up to 217 meters and weighs about 73,000 tons, the equivalent of a small aircraft carrier. But what's truly astonishing isn't just the size, it's the near-perfect precision. Each segment is precast on land under strict quality control to ensure that when connected underwater, the joints are sealed so tightly that not a single drop of seawater can get through. The process begins by towing the tunnel segments out to sea on massive floating pontoons, resembling a long train drifting across the ocean. Once in position, specialized cranes lower each segment into a pre-dredged trench on the seabed where even a few centimeters of misalignment could put the entire structure at risk. To ensure watertight and safe connections, engineers use special rubber gaskets compressed tightly between joints. But even when sealed perfectly, an invisible enemy remains. Archimedes' upward force, the buoyancy of seawater that constantly tries to lift the tunnel back up. The solution? A thick blanket of sand and gravel is laid over the tunnel roof like a heavy quilt, pinning it permanently to the seabed. The entire structure now resembles a sleeping steel dragon beneath the ocean, silent yet unshakable. However, immersed tube tunneling isn't always feasible. When faced with strong ocean currents, swirling sediments, or complex seabed topography, stabilizing such massive segments becomes nearly impossible. In those cases, engineers are forced to switch strategies. And that's when a different technology is deployed, one that's more powerful, more flexible, and capable of boring through places once thought unreachable. The TBM method, using giant tunnel boring machines that work like robotic moles under the ocean floor. But this method only works when the seabed is relatively flat, currents are stable, and the weather is favorable. So what happens when you need to tunnel beneath a strait with jagged seabeds, rushing water, or constantly shifting weather conditions? In such cases, China rolls out its next option using enormous machines called tunnel boring machines, or TBMs. Imagine a steel worm over 100 meters long, with a rotating circular cutter head fitted with more than 140 steel blades, spinning like a stone mill at nearly 3 revolutions per minute. The cutting pressure can reach 400 bars, enough to crush hard limestone or thick clay. But the most remarkable part is this: the entire process of excavation, lining, grouting, and machine advancement happens continuously in a sealed underground system. In soft or water-saturated soils, engineers inject a mixture of foam and water into the cutter chamber to balance the pressure, a critical step to prevent tunnel collapse. After each 1.5-meter segment is bored, the system automatically installs concrete rings and injects grout to fill any voids between the structure and surrounding soil. On average, a TBM can advance 15-20 meters per day, slow but steady and extremely safe. This is why the method is preferred for long tunnel stretches that must last for decades, even centuries. However, TBMs aren't always the ideal solution. When the geology includes ultra-hard rock or pressurized gas pockets where cutter heads might shatter under the stress, TBMs become too risky. At that point, crews must fall back on a traditional but hazardous method: controlled drill and blast. It may sound like an action movie, but it's actually a highly precise equation of physics and timing. Engineers drill deep holes into the rock, insert explosives, and detonate them in micro-delayed sequences, each blast separated by milliseconds to maximize rock breakage while minimizing shockwaves. A single blast can fracture 1.5 meters of rock, and crews can perform up to 18 blasts per day. But do you know what's truly dangerous in this method? It's not the blast itself, it's what comes after. Every explosion sends shockwaves that can crack the surrounding rock, threatening the structural integrity if not reinforced in time. On top of that, working near sensitive marine ecosystems means monitoring noise and pressure levels to avoid mass die-offs of sea creatures. That's why drill and blast is always the last resort, used only when both TBM and immersed tube methods are unfeasible. And then, there's one more method, simple, manual, yet often the last lifeline in the most extreme conditions: traditional excavation. When you can't blast, can't deploy robots, and can't immerse prefabricated segments, you dig meter by painstaking meter. Of course, no one's using shovels like in medieval times. Instead, engineers dig vertical shafts from the surface down to the tunnel point, using hydraulic cutters to break soil and rock, while immediately spraying concrete, installing steel arches, and bolting supports to stabilize the structure. In this process, pressure is everything. If the pressure inside the tunnel is even slightly lower than the surrounding seawater, even a small gap, water will flood in at terrifying speed. That's why the entire system is monitored by sensors, pressure valves, and 24/7 engineering teams checking every single data point. All these methods, from immersed tube to TBM, to drill and blast to manual excavation, don't stand alone. They form a flexible sequence of choices, calculated from the very first geological survey, and are constantly switched based on real-time conditions or surprises. When the final meters of the tunnel are connected beneath the seabed, it may seem like the project is done, but in reality, it's only the beginning. An undersea tunnel must not only remain stable on its grand opening day, but it must also continue to operate safely, smoothly, and reliably for decades to come, in an environment where pressure, humidity, temperature, and even seismic activity can change by the hour. That's why, after finishing the reinforced concrete structure, Chinese engineers move on to the next critical phase: interior completion. This is not just building a passageway, it's creating a fully self-sustaining operational ecosystem, one that can monitor itself, detect errors, and even maintain itself without fully relying on human operators. The entire tunnel is divided into two independent traffic levels, one for vehicles traveling in direction A and the other for direction B. This instantly doubles the traffic capacity without needing to expand the excavation size. Between these two lanes, a network of escape routes and ventilation shafts is integrated, ensuring that anyone on foot is always within 200 meters of an emergency exit or rescue station. On the tunnel walls, hundreds of LED lights, waterproof, corrosion-resistant, and heat-proof, provide continuous illumination 24/7. The tunnel floor is coated with anti-slip, fire-resistant materials, with drainage systems designed to immediately redirect water in the event of leaks. Every 100 meters, infrared cameras and toxic gas sensors monitor air quality and can detect smoke, fire, or vehicle breakdowns in real time. But the true heart of the entire safety system isn't what you see, it's what's hidden inside the concrete. A smart network of Industry 4 sensors runs along the full length of the tunnel, measuring pressure, humidity, temperature, vibrations, and even seismic acceleration, all streamed live to the operations control center. If even the slightest abnormal vibration occurs, as small as 1/10 of a Richter scale degree, the system automatically cross-checks the data and alerts engineers. If early signs of structural fatigue or hairline cracks are detected, a maintenance team is dispatched to the exact location even before citizens or cameras know something's wrong. At the same time, specialized maintenance robots, equipped with omnidirectional wheels, LiDAR sensors, and robotic arms, regularly scan areas the human eye or camera can't see. Some robots can even spray concrete or seal cracks on the spot, minimizing the need for full tunnel closures. At tunnel entrances, engineers install automated barricade systems that can seal off access in seconds during fire, flooding, or collisions. Ventilation clusters are also deployed throughout, with powerful jet fans capable of clearing the entire tunnel of smoke or gas in 5-7 minutes. Not only are people and machines constantly monitoring the tunnel, but the system is also connected to AI software that analyzes driver behavior. It can detect drowsiness, brake failures, or vehicle overload risks in real time. Thanks to this, over the years of operation, these tunnels have maintained an incredibly low, near-zero accident rate. Yet no matter how advanced the technology becomes, human oversight still plays a critical role. Hundreds of maintenance engineers, safety supervisors, and environmental experts are stationed at underground control points along the route. They're ready to intervene manually at any moment, forming the final layer of protection. No structure is perfect forever. But with smart monitoring, automated operation, and humans at the helm of technology, China is gradually transforming its undersea tunnels into living masterpieces, tunnels that can breathe, sense, and heal themselves over time. For centuries, the ocean was considered humanity's final boundary. But now, with each meter of tunnel laid beneath the seabed, each massive segment lowered with precision down to the centimeter, China is turning the impossible into reality. From tunnel segments weighing tens of thousands of tons, immersed with surgical precision, to rock-crushing robots that look like machines from science fiction, Every step in this construction process is not just a technical challenge, but a declaration from humanity to nature. We are not here to conquer, we are here to coexist, adapt, and overcome. This is not merely a transportation tunnel. It is an economic artery, a lifeline of connection, a living symbol that engineering no longer stops at the shoreline. The undersea tunnels China has built and continues to build stand as a powerful commitment that humanity will keep moving forward, even when the obstacles lie hundreds of meters beneath the waves. Today's underground construction is no longer just about mechanical strength. It is the seamless fusion of engineers, machinery, Industry 4, and artificial intelligence. And thanks to that, a structure once deemed impossible can now operate for decades safely, precisely, and intelligently maintained in real time. What do you think about this incredible undersea construction technology? Which method impressed you the most? Don't hesitate to leave your thoughts below. We'd love to hear your perspective. And if this video helped you see modern engineering in a new light, don't forget to hit the subscribe button for Massive Minds, where we tell extraordinary stories of the world's greatest engineering feats. And every project is a heroic tale between human intelligence and the limits of nature.